What's up, math lads? Today's a good day to celebrate. Episode 6 is here, even if your paycheck isn't. And we're continuing where we left off last week when we talked about functions. Functions are a big topic. They're everywhere in math, and they never go away. They're not particularly fun all the time, but with enough time, patience, and Stockholm Syndrome, you'll learn to embrace them. So you're closing in on your final exam. You've prepped, studied, and watched a dozen Khan Academy videos just to reestablish your pre-foundations foundations. You're hopeful and ready to take on the challenge because nothing can be worse than the challenges you already faced. Just wait until grad school. Before throwing more of your dreams into a NutriBullet, there's one hope: watching more Koshi's Couch. From last week, we're going to divert slightly to analyzing function composition. Function composition, loosely speaking, is the idea of chaining functions together by looking at functions within functions. Confused yet? Let's put it this way. Suppose I have an input that goes into one function and spits out the output. Then I take that output and make it the input to another function. That's the process of composing functions. This kind of thing might be important to an application of facial recognition, where maybe we have an input image and a function that detects whether a face is present. Then, from the face, another function determines the mood. So if I were to take my own face and run it through this composition of processes, then it would return no face detected, because the deep learning algorithm wasn't trained to handle perfect tens. And by perfect tens, I mean mod 10. Let's add some rigor to this. If f is a function from a to b, and g is a function from b to c, then the function g composed of f is a function from a to c. When we represent them in algebra courses, they're typically thought of as inner and outer functions. So for example, if f of x equals x cubed, and g of x equals 4x plus 9, then g of f of x is equal to 4x cubed plus 9. Likewise, f of g of x is the quantity 4x plus 9 cubed. Now there's something convenient about our previous definitions of injections and surjections from the previous video. As it turns out, if f and g are both injections, then g composed with f is an injection. If they're surjections, then the composition is surjective. And assuming the first two are definitely true, and I'm not lying to you in any capacity, then it must be true that if f and g are bijections, then g of f is also a bijection. Let's prove these facts, because at this point you have the means to understand them. First, suppose we have three sets, a, b, and c, where f maps from a to b and g maps from b to c. We need to show that if we assume g of f of a1 equals g of f of a2, this implies that a1 equals a2. Well, if g of f of a1 equals g of f of a2, then f of a1 equals f of a2 since g is injective. But f of a1 equals f of a2 implies that a1 is actually a2 since f is injective. Therefore, g of f must be injective. Now let's look at surjectivity. We need to show that for any c and c, there exists an a and a such that c equals g of f of a. Let's see b and c. Since g is surjective, there exists a b in b such that g of b equals c. But since f is surjective, there exists an a such that f of a equals b. So, there exists an a such that g of f of a equals c. So now we can throw our bijective mappings around like it's everyone's business, like the local band that has a totally new and original sound, and doesn't in any way, shape, or form sound like a watered-down, low-budget version of the prog band they're trying to be. But mathematicians would never tout on about the clever new proof of a theorem that was already proven but slightly more directly and kind of less elegantly. Moving on, let's talk about inverse functions. So we talked about mapping inputs to outputs, but we never stopped to ask the question, what if we flip the picture? Well, hold on. A couple of conditions. Note that if a function is not one-to-one, then there's two outputs that correspond to the same input. If that output becomes an input, then there's an element that maps to two different elements. Then you don't have a function, you have garbage. Toss it, burn it, and watch it till it's ashes. Then do the same with the rest of your homework and tell your professor that someone on the internet told you to do it, and then show them this video. But the problems only get worse. If a function isn't onto, then that means the new domain will have an input that doesn't map anywhere. This is another problem that we frankly don't need to dive into. So in order for the inverse function to exist, you need the function to be bijective. So, if you set yourself up properly, you can undo all of your mistakes. So that's how politicians get reelected. So how do we find inverse functions? Well, first let's recall that functions are a mapping, but more succinctly, they are sets of ordered pairs. The inverse function is the flip set of ordered pairs. Suppose we compose a function with its inverse, then we should return the identity function. So for example, if f is a function from r to r, where f of x equals 12x plus 17, we must prove this is a bijection. Then all we have to do is replace f of x with y, swap the input and output, and solve for y. Then y should be x minus 17 over 12. If we compose our new functions with our old one, then we should see it simplify to x, regardless of the order of the compositions. So let's talk about some different types of functions. Binary operations are examples of functions. Addition, multiplication, subtraction, functions. Yes, I'm going to ruin your first grade math class by formalizing it. I'm not sorry. Let's consider a function which we'll call plus, that takes an input from the domain z cross z and maps it to an output in the codomain z. Now let's define it by plus of ab equals a plus b. In other words, plus of 6 and 9 equals 15, and plus of 4 of 20 equals 24. Is this map injective? Well, no, because plus of 1 and 2 is equal to plus of 2 of 1 is equal to plus of 3 and 0 is equal to plus of 5 and negative 2, and so on. But the function is certainly surjective. This is because for every integer in the codomain y, you can use the input y0 from the domain to get to y. Another example of a function you might consider is an infinite sequence. What? But with sequences you just list things out. How is that a function? You might protest with great frustration remembering the nightmares you had from taking pre-calculus. Well, listing the elements of a sequence is a function. Consider a function a from n to r, where a of n is a sub n, or the nth term of a sequence. Let's say, for example, a sub n is 1 over n. If we write out some of the elements, then a of 1 equals 1, a of 2 equals 1/2, a of 3 equals 1/3, and so on. Is this injective? Yes. Is it surjective? Well, no, since r is our codomain, and our range is unit fractions between 0 and 1. As an aside, under this context, you might form a bijection from n to some set by finding a sequence that contains every element of a set only once. But that's for a later video. At this point, you should have a more complete picture of how functions work in several different scenarios. Now you're ready to take on the world. Maybe embrace some creative projects, or learn to handle yourself emotionally and track your mental health. Perhaps get a job and live a healthy lifestyle. Who am I kidding? You chose to study math. You're not going to have any of those things. But one can dream. Thanks for taking the time to watch this video. If you enjoyed the video, please give it a thumbs up and share with your friends. Please comment your thoughts down below, and I'll see you next time. Keep learning.